Hello and welcome. In this video, we'll be diving deep into the world of polynomials, covering several key concepts that are fundamental to IB, AA, HL mathematics. By the end of this session, you will be able to define and distinguish between zeros, roots, and factors of a polynomial. You'll also learn how to use the remainder and factor theorems to solve problems, understand the profound implications of the fundamental theorem of algebra, and finally, you'll be able to sketch and find the equations of cubic and quartic polynomials from their graphs. Let's get started with our first topic. First, let's clarify some essential terminology: zeros, roots, and factors. A zero of a polynomial p of x is any value of the variable x that makes the polynomial equal to 0. In other words, if you substitute a value alpha into the polynomial and the result is 0, then alpha is a 0. The roots of a polynomial equation are simply the solutions to that equation. So, if you have the equation p of x equals 0, the values of x that satisfy it are the roots. This means that the roots of the equation p of x equals 0 are the same as the zeros of the polynomial p of x. Geometrically, the real roots of the equation p of x equals 0 correspond to the x-intercepts of the graph of y equals p of x. These are the points where the graph crosses or touches the x-axis. Let's look at an example to make this concrete. Consider the polynomial p of x equals x cubed plus 2x squared minus 3x minus 10. Let's evaluate this polynomial at x equals 2. We substitute 2 for x, 2 cubed plus 2 times 2 squared minus 3 times 2 minus 10. This simplifies to 8 plus 8 minus 6 minus 10, which equals 0. Because p of 2 equals 0, we can conclude several things. First, 2 is a zero of the polynomial p of x. Second, 2 is a root of the equation p of x equals 0. And third, the graph of y equals p of x has an x-intercept at x equals 2. Now, what about factors? A linear factor of a polynomial p of x is an expression of the form x minus alpha, where alpha is a zero of the polynomial. This means that if x minus alpha is a factor, you can write p of x as the product of x minus alpha and some other polynomial, q of x. For example, if a polynomial is given in factored form, like p of x equals the product of x plus 1, 2x minus 1, and x plus 2, then each of these expressions is a linear factor. The zeros would be minus 1, 1/2, and minus 2. So to recap, a zero is a value that makes the polynomial 0, a root is a solution to the polynomial equation, and a factor is an expression that divides the polynomial evenly. They are all closely related concepts. Let's practice finding zeros. Our objective here is to find the zeros of a polynomial, which means solving the equation p of x equals 0. First, let's find the zeros of the quadratic x squared minus 4x plus 53. To do this, we set the polynomial equal to 0. Since it's a quadratic, we can use the quadratic formula. The formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. In our case, a is 1, b is minus 4, and c is 53. Substituting these values, we get x equals 4 plus or minus the square root of negative 196 all over 2. The square root of negative 196 is 14i, where I is the imaginary unit. So x equals 4 plus or minus 14i divided by 2. Dividing by 2, we find the zeros are 2 plus 7i and 2 minus 7i. Notice that these are a complex conjugate pair. Now for a cubic polynomial. Let's find the zeros of z cubed plus 3z. Again, we set the polynomial to 0. This time, we can factor out a common term, z. This gives us two factors, z and z squared plus 3. Setting the first factor to 0 gives us z equals 0. For the second factor, z squared plus 3 equals 0, we get z squared equals minus 3. Taking the square root of both sides, we find z equals plus or minus I times the square root of 3. So the three zeros of this cubic polynomial are 0, I times the square root of 3, and negative I times the square root of 3. Again, we see a complex conjugate pair. We have now successfully found the zeros of both a quadratic and a cubic polynomial, including complex zeros. Next, let's explore polynomial equality. Our goal is to use the principle of equating coefficients to find unknown constants within a polynomial expression. The core idea is simple. Two polynomials are equal if and only if they have the same degree and the coefficients of their corresponding terms are equal. This means the coefficient of x squared on one side must equal the coefficient of x squared on the other, and so on. Let's work through an example. We are given that 6x cubed plus 7x squared minus 19x plus 7 is equal to the product of 2x minus 1 and ax squared plus bx plus c. We need to find the constants a, b, and c. First, we expand the right-hand side. We multiply each term in the first bracket by each term in the second. This gives us 2ax cubed plus 2bx squared plus 2cx minus ax squared minus bx minus c. Next, we group the terms by their powers of x. We have a cubic term, a quadratic term, a linear term, and a constant term. Now, we can equate the coefficients of the corresponding powers of x on both sides of the equation. For the x cubed terms, we have 2a equals 6, which means a must be 3. For the constant terms, we have 7 equals negative c, so c must be minus 7. Now we use the coefficients of the x squared and x terms. For x squared, 2b minus a equals 7. For x, 2c minus b equals minus 19. We can substitute the values of a and c we just found into these equations. Using the x squared equation, 2b minus 3 equals 7, which gives 2b equals 10, so b equals 5. We can check this with the x equation. 2 times minus 7 minus 5 equals minus 14 minus 5, which is minus 19. This matches the left side, so our values are correct. Therefore, the constants are a equals 3, b equals 5, and c equals minus 7. We have successfully used polynomial equality to find the unknown coefficients. Now we move on to two of the most powerful tools in polynomial algebra, the remainder theorem and the factor theorem. The remainder theorem states that when a polynomial p of x is divided by a linear factor x minus k, the remainder is simply p of k. This means you don't have to perform long division to find the remainder. You can just substitute the value k into the polynomial. Let's prove this. By the division algorithm, we can write any polynomial p of x as the product of the divisor, x minus k, and some quotient polynomial q of x, plus a remainder r. So p of x equals q of x times the quantity x minus k plus r. Now, let's substitute x equals k into this equation. We get p of k equals q of k times the quantity k minus k plus r. Since k minus k is 0, the entire first term vanishes, leaving us with p of k equals r. This proves the theorem. Let's see it in action. Find the remainder when x to the power of 4 minus 3 x cubed plus x minus 4 is divided by x plus 2. Here, our divisor is x plus 2, which we can write as x minus negative 2, so k is minus 2. According to the remainder theorem, the remainder is p of minus 2. We substitute minus 2 into the polynomial. Negative 2 to the power of 4 minus 3 times negative 2 cubed plus negative 2 minus 4. This calculates to 16 plus 24 minus 2 minus 4, which equals 34. So the remainder is 34. The factor theorem is a direct consequence of the remainder theorem. It states that k is a zero of a polynomial p of x if and only if x minus k is a factor of p of x. This is because if k is a zero, then p of k equals 0. By the remainder theorem, this means the remainder when dividing by x minus k is 0. And if the remainder is 0, then x minus k must be a factor. Let's use the factor theorem. Find the constant k given that x minus 2 is a factor of x cubed plus k x squared minus 3x plus 6. Since x minus 2 is a factor, the factor theorem tells us that p of 2 must be 0. We substitute 2 into the polynomial and set it equal to 0. This gives us 8 plus 4k minus 6 plus 6 equals 0, which simplifies to 8 plus 4k equals 0. Solving for k, we find k equals minus 2. We have now seen how the remainder and factor theorems provide powerful shortcuts for working with polynomials. Let's now turn our attention to the fundamental theorem of algebra, a cornerstone of polynomial theory. This theorem, first proven by Carl Friedrich Gauss, has two main parts. First, it guarantees that every polynomial of degree n greater than or equal to 1 has at least one zero, which can be a complex number. Second, and more importantly for us, it states that a polynomial of degree n has exactly n zeros when counted with multiplicity. This means a cubic polynomial has exactly 3 zeros, a quartic has exactly 4, and so on. These zeros can be real, complex, or a combination of both. A crucial property for real polynomials, which are polynomials with real coefficients, is the conjugate root theorem. It states that if a complex number p plus qi is a zero of a real polynomial, then its conjugate, p minus qi, must also be a zero. This means complex zeros of real polynomials always come in conjugate pairs. This is a very powerful tool for finding zeros. Let's use this. Suppose minus 3 plus I is a zero of the real polynomial p of x equals ax cubed plus 9x squared plus ax minus 30. We need to find a and all the zeros. Since the polynomial is real and minus 3 plus I is a zero, the conjugate root theorem tells us that its conjugate, minus 3 minus I, must also be a zero. These two complex zeros come from a quadratic factor. We can find this factor by using the sum and product of the roots. The sum is minus 6, and the product is 10. This gives us the quadratic factor x squared minus the sum times x plus the product, which is x squared plus 6, x plus 10. Now we can write the polynomial in factored form. Since it's a cubic, it must have one more linear factor. We can write p of x as the product of our quadratic factor and a linear factor, ax minus 3. We know the leading coefficient is a, and the constant term is minus 30, which must be the product of 10 and minus 3. Expanding this, we get ax cubed plus 6a minus 3 x squared plus 10a minus 18 x minus 30. Now we equate the coefficients of x squared from this expansion to the original polynomial. We get the equation 6a minus 3 equals 9. Solving for a, we find a equals 2. We can check this with the x coefficients. 10 times 2 minus 18 equals 2, which matches the original polynomial. So a equals 2. Now we have the full polynomial. P of x equals 2x cubed plus 9x squared plus 2x minus 30. The zeros are the two complex conjugates we found, minus 3 plus I and minus 3 minus I, and the 0 from the linear factor 2x minus 3, which is 3 halves. This example beautifully illustrates how the fundamental theorem of algebra and the conjugate root theorem work together to help us find all the zeros of a polynomial. Let's continue our exploration of polynomial properties with the sum and product of roots theorem. You might remember this for quadratic equations. For a quadratic ax squared plus b, x plus c equals 0, the sum of the roots is negative b over a, and the product is c over a. This theorem generalizes to polynomials of any degree. For a general polynomial equation of degree n, the sum of the roots is always negative a sub n minus 1 divided by a sub n. The product of the roots is negative 1 to the power of n times a sub 0 divided by a sub n. Let's apply this to an example. Find the sum and product of the roots of the cubic equation. 2x cubed minus 7x squared plus 8x minus 1 equals 0. First, let's identify our coefficients. The leading coefficient, a sub 3, is 2. The coefficient of x squared, a sub 2, is minus 7. And the constant term, a sub 0, is minus 1. The sum of the roots is negative a sub 2 over a sub 3. This is negative minus 7 over 2, which simplifies to 7 halves. The product of the roots is negative 1 to the power of 3 times a sub 0 over a sub 3. This is negative 1 times minus 1 over 2, which gives us 1 half. This theorem is incredibly useful, especially when you know some of the roots and need to find others, or when you need to relate the roots to the coefficients without solving the entire equation. Now, Let's bring together everything we've learned to analyze and sketch the graphs of cubic polynomials. Our objective is to understand the relationship between the factors of a cubic polynomial and the shape of its graph. A cubic polynomial can be categorized into four main types based on its zeros. The leading coefficient, a, determines the end behavior. If a is positive, the graph starts low on the left and ends high on the right. If a is negative, it starts high and ends low. Type 1 has three distinct real zeros. The graph will cross the x-axis at three different points. Type 2 has two real zeros, one of which is repeated. The graph will touch the x-axis at the repeated zero and cross it at the other. Type 3 has one real zero repeated three times. The graph will cross the x-axis at that point, but it will be flat or have a horizontal tangent there. Finally, type 4 has one real zero and two complex conjugate zeros. The graph will only cross the x-axis once. Let's find the equation of a cubic from its graph. Consider this graph. It crosses the x-axis at -1, 2, and 4. It also passes through the y-intercept at -8. Since the graph crosses the x-axis at -1, 2, and 4, these are the zeros. This means the factors are x plus 1, x minus 2, and x minus 4. So the equation must be of the form y equals a times the product of these factors. To find the value of a, we use the y-intercept. When x is 0, y is -8. Substituting these values, we get -8 equals a times 1 times -2 times -4. This simplifies to -8 equals 8a, so a equals -1. Therefore, the equation of the cubic is y equals negative the quantity x plus 1 times x minus 2 times x minus 4. The negative sign for a is consistent with the graph's end behavior, starting high and ending low. By analyzing the x-intercepts and the y-intercept, we can reconstruct the equation of a cubic polynomial. Let's extend our graphing skills to quartic polynomials. Our objective is to understand the different shapes of quartic graphs based on their factors. A quartic polynomial has a degree of 4, so it has exactly 4 zeros. The leading coefficient, a, determines the end behavior. If a is positive, the graph opens upwards, like a, w, or u. If a is negative, it opens downwards, like an m. The behavior at the x-intercepts is determined by the multiplicity of the factors. A single factor, like x minus alpha, means the graph cuts the x-axis. A squared factor, like x minus alpha squared, means the graph touches the x-axis at alpha, forming a local minimum or maximum. A cubed factor means the graph cuts the x-axis at alpha, but is flat there. A quadruple factor means the graph touches the x-axis and is flat at that point. Let's find the equation of a quartic from its graph. Consider this graph. It touches the x-axis at -1 and cuts the x-axis at -3 and 3. It also passes through the y-intercept at -3. The fact that the graph touches the x-axis at -1 tells us that x plus 1 is a repeated factor, specifically squared. The cuts at -3 and 3 give us the factors x plus 3 and x minus 3. So the equation is y equals a times the quantity x plus 1 squared times x plus 3 times x minus 3. To find a, we use the y-intercept, 0, -3. Substituting these values, we get -3 equals a times 1 squared times 3 times -3. This simplifies to -3 equals -9a, so a equals 1/3. The equation of the quartic is y equals 1/3 times x plus 1 squared times x plus 3 times x minus 3. The positive value of a is consistent with the graph opening upwards. Understanding the end behavior and the behavior at the x-intercepts is key to sketching and finding the equations of quartic polynomials. Finally, let's discuss a practical method for finding the exact zeros of a polynomial when you can't easily factor it. This method combines technology with algebra. Our objective is to use a graphing calculator or software to find a rational zero, and then use that to factor the polynomial and find the remaining zeros. Let's find the exact zeros of the polynomial p of x equals 3x cubed minus 14x squared plus 5x plus 2. First, we graph the polynomial using technology. We look for any x-intercepts. In this case, the calculator shows an intercept at approximately 0.666667. This is a decimal representation of the fraction 2/3. So, we suspect that x equals 2/3 is a 0. By the factor theorem, this means that x minus 2/3 is a factor. To avoid fractions, we can multiply by 3 to get the factor 3x minus 2. Now we know that p of x can be written as the product of 3x minus 2 and some quadratic factor x squared plus ax minus 1. We can find the unknown coefficient a by expanding the right side and equating coefficients, just like we did before. Expanding gives us 3x cubed plus 3a minus 2x squared plus minus 3 minus 2ax plus 2. Equating the x squared coefficients, we get 3a minus 2 equals minus 14, which gives a equals minus 4. Equating the x coefficients, we get minus 3 minus 2a equals 5, which also gives a equals minus 4. The values are consistent. So we have factored the polynomial into 3x minus 2 times x squared minus 4x minus 1. We already know 1, 0 is 2/3. To find the other two, we set the quadratic factor to 0 and use the quadratic formula. The quadratic formula gives us x equals 4 plus or minus the square root of 20 all over 2. This simplifies to 2 plus or minus the square root of 5. So the three exact zeros are 2/3, 2 plus the square root of 5, and 2 minus the square root of 5. This method is a powerful combination of graphical analysis and algebraic techniques, allowing us to find exact zeros even for complex polynomials. We've covered a lot of ground today. Let's quickly recap the key ideas. We started by defining zeros, roots, and factors, understanding their interconnectedness. We then learned how to use polynomial quality to find unknown coefficients. The remainder and factor theorems provided powerful shortcuts for division and factorization. The fundamental theorem of algebra and the conjugate root theorem gave us a framework for understanding the number and nature of zeros. We also saw how to use the sum and product of roots theorem. Finally, we developed the skills to sketch and find the equations of cubic and quartic polynomials from their graphs, and to find exact zeros using a combination of technology and algebra. These concepts are essential for your success in IBDAHL mathematics. Now, it's your turn to practice. Here are 5 practice questions for you to work through. Pause the video and give them a try. The answers will appear shortly. Here are the answers. Check your work and make sure you understand any mistakes you might have made. Keep practicing and you'll master these concepts in no time. Thank you for watching.